Welcome to our experiment video. I am Jasmine Asinin and I'm from Group 2. My group consists of 4 members, which are myself, Jasmine, Jijo Sinwayam Posong, Keshvini Raguraman, and also Muhammad Shafiq bin Muhammad Rafi. Today we are going to present experiment 2 with the title of Single Stage Compressor. So firstly, I'm gonna talk about the theory of this experiment. In this slide, I'm showing figure 1. In this figure 1, it is a standard single stage vane compressor. So in figure 1, as you can see, a fixed volume of air is trapped between two sliding vents driven by an offset rotor. This volume of air is then pushed to the outlet where the area and also volume is reduced, and therefore its pressure becomes higher and it is squeezed out of the outlet port. All the formula used in calculating the results in this experiment will be further explained by my other member. So without further ado, we will pass the next slide to the next person.
So I will proceed with the apparatus of the experiment. So as you can see, this is basically one set of a single stage compressor. So it has a plenum chamber 1 and 2 for suction and deliver, air pressure in and out, temperature of air in and out, outlet and inlet pressure control valve, the compressor itself, a spring balance, a flow meter, electronic motor, and other minor parts. For the experimental procedure, first the power was switched on and then the green inlet valve was opened by turning the valve anti-clockwise. The initial readings for all parameters listed in table 1 was recorded at the beginning of the experiment. Then the tachometer was used to record the motor speed and moving on. The motor was switched on, then the compressor outlet pressure P2 was set to 1 bar gauge by using the red outlet valve. The valve was turned clockwise to increase the pressure. Next, the spring balance was adjusted to ensure that the indicator on the motor is between two black lines prior to record any motor force values. Lastly, the temperature of the outlet air T2 was recorded 1 minute interval. So, to stop the experiment, first, the compressor outlet pressure P2 was reduced to 0 bar gauge using the red outlet valve by turning the valve anti-clockwise to decrease the pressure. Last but not least, the motor and the power was switched off.
Hi, I am Keshwini. Now I will present the result calculation part for experiment 2. So first of all, the data given is the length of top arm, which is 0.2 meter. Then compressor swap volume 267 cm cube per cubic REV, and specific heat capacity of air at 1005 joule per kg Kelvin. Next, for the parameters given with the initial readings, like the air temperature into apparatus, the T0 is 29 degrees Celsius, the air temperature into compressor T1 is 28 degrees Celsius, then the air temperature out of the compressor T2 is 27 degrees Celsius, the atmospheric pressure from barometer PO is 1.025, vacuum into compressor gauge P1 is 0.6 bar, then the air pressure out of the compressor gauge P2 is 1 bar. Next, the flow meter is 300, motor speed is 1450, motor spring balance is 2.7, and the electric power is 1.18 times 10 to the power of 3. So that is the parameters for the single stage compressor. Now for the calculation part, first the volumetric flow rate is calculated with the formula and the result is 0.005, followed by the specific volume through flow meter with the R constant at 0.287. The result obtained is 0.84602. Then the mass flow rate is calculated to be 0.00591. the energy added to the air by the compressor, the equation obtained is the energy added equals to 0.00591 times 1005 times T2 minus 28 times W. For the power out of the motor is calculated to be 804.37652. Thus, the heat emitted from the compressor, which is the QC, is equals to 804.37652 minus HC times W. So now, to obtain the result of the set of data given, the formula energy added to air compressor is used by substituting the values of T2 given. However, the heat emitted from the compressor is calculated by substituting the HC value calculated before to obtain the values of QC. Therefore, following the same method throughout calculating the HC and QC, thus the table will be complete. So three graphs were plotted after the calculation of data. The first graph is the T2 temperature versus time graph. Graph 2 is energy added to air by compressor versus time, and graph 3 is heat emitted from the compressor versus time. And that's all for the result part. So I'll let the next person to continue.
Hello, my name is Chicha Sinwa, and today I'll be talking about this discussion. So now let us move on into the second part of the discussion. So what is happening to the energy that is being input into the system as it heats up? So the compressor heats the air, causing an increase in temperature up until a point where it stabilizes, reaching thermal equilibrium. So this illustrates the energy being input to the system is absorbed by the system, and energy is lost to the surrounding in the form of heat. Finally, we will move on to the third part of the discussion. So how does the amount of energy lost as heat compared to the work input of the compressor and the heat added to the air? Comparing the amount of energy lost as heat with the work input to the compressor, the amount of energy lost as heat is smaller. The energy lost as heat, on the other hand, is smaller compared to the heat applied to the air. The heat generated by the compressor was the heat loss in this experiment, while the energy applied to the air by the compressor was the usable energy used to compress the air. The work input to the compressor was supplied by the motor's output power, which remained constant throughout the whole experiment. So energy input was converted into heat released by the compressor and energy applied to the air in this experiment. So according to our data, the higher the temperature difference, the more energy is applied to the environment, and the lower the energy loss. This means the compressor has a higher efficiency in higher temperatures. So the first one is, why does the heating curve take the shape of what it is now? So there were three graphs that were plotted in this experiment. The first one being the outlet temperature against time, the energy applied against time, and finally the heat released by the compressor against time. So graph 1 and graph 2 showed an increase in data, which signifies a heating up curve. Graph 3, on the other hand, showed a decrease in data, which means it had a heating down curve. Heat transfer into a system increases the energy molecules and thus is the internal energy of the system, while heat transfer from a system decreases the energy. Now moving on to graph 2. Based on graph 2, we can see that the value of energy applied to the air by the compressor has risen over time. This occurs because the compressor's operation provided enough energy for the pressure for the air to exit the compressor. A greater energy applied to the air by the compressor results in additional work by the compressor, which can cause the compressor to take a longer time to work.
Okay, now I will state the conclusion made from this experiment. To summarize, according to the experiment, after 31 minutes of heating, the outlet temperature T2 steadily rises and remains steady. This demonstrates how quickly the air is heated by a single stage compressor. The amount of energy added to the air by the compressor HC increases exponentially during the heating process, but the amount of heat emitted by the compressor QC decreases with time. This is due to the possibility of energy losses as input energy is transformed to heat, sound, or even used to pump air. The compressor added 6 to 9.5923 watt of energy and emitted 174.78422 watt of heat, resulting in a steady state at T, T equals to 31 minutes. The temperature will likewise drop if the compressor outlet pressure P2 is dropped to zero point 0.5 bar. As a result, the compressor's heat output QC will be lowered. That's all from us. Thank you.